Hi, I'd like to talk about TCP/IP and socket programming in this lecture, along with giving you some ideas about how the addressing works at the transport and the network layer. So we were talking about TCP and UDP, the two dominant transport layer protocols in today's internet, describe how they address application through ports, describe how demultiplexing works, that is, how a machine, a host, decides to which application a packet needs to be delivered to. We'll look more specifically at how IP addresses are being assigned and used, and we look at what it takes to support protocol independence, that is, the ability to support both IP version 4 and IP version 6. And we'll be talking about the so-called socket API, which is the API that is used to write network applications. And having a working knowledge of the socket API is really a basic skill, I think, for every practicing computer scientist. We will be looking at the transport and network layer in particular. Here I am showing the 5-layer Internet Protocol stack application all the way down to physical layer, and we will be looking specifically at the transport and network layer. At the transport layer, the two dominant protocols, UDP and TCP. TCP provides reliable data transmission. UDP provides unreliable or best effort data transmission. Here, port numbers are used to address applications that may make use of this transport layer. Now, the network layer, this is where IP version 4 or IP version 6 is being used. This is where different hosts are being addressed through IP addresses. Okay? And so notice that the TCP and UDP protocols are designed to be used in conjunction with IP. That's why they're often called TCP/IP or UDP/IP. And specifically, they make use of the addresses at the network layer. So they do not define their own addresses, but rather they use IP addresses. So for IP addresses, you can think of those addresses as addressing hosts or the endpoints, machines. But as we will see, IP addresses actually will address network interfaces on hosts, and we'll see the difference between those shortly. Let's talk about the first one, UDP. UDP is the user datagram protocol. It was designed a long time ago in the 1980s. It is super simple. The specification fits on 2 pages. It is described in RFC 768, which is still valid today by and large. It is a datagram-oriented protocol. So in UDP, a sender can send a message called a datagram that can be up to 64 kilobytes large, and it is delivered as a whole at the receiver, but it may not be delivered because the protocol does not guarantee reliability. It just makes the best effort. UDP is what we say is a connectionless protocol. That means no connection setup is required for a sender to send a datagram to a server or receiver. UDP also supports multicast as an aside where a packet can be broadcast to multiple receivers. Here at the bottom, I'm showing the UDP datagram header. That is the part that is the added by the UDP protocol at layer 4. So this shows those parts that are necessary to address applications. In this case, the destination port and the source port. It also stores the length of the packet, and it stores a simple checksum, the so-called internet checksum. It's a very simple algorithm that can be used to compute this checksum, and that ensures end-to-end integrity, or at least it makes it possible to detect certain types of bit errors. The internet checksum is not a very strong checksum, but it provides an additional way to detect whether the data was delivered correctly. TCP, on the other hand, is much more complex than UDP. TCP was developed in the 1970s. The first specification describing TCP dates back to 1981, RFC 793. During the 1980s, TCP was started being deployed, and a lot of experience was gained in implementing it, and that led to improvements. the most notable of which was the addition of congestion control in RFC 1122 in 1989. Since then, many additions or optional options have been proposed to TCP, and you can see RFC 7414, which was published in 2015, for a roadmap to all the specifications, the RFCs that describe TCP today. So let's talk about TCP. So TCP is a point-to-point protocol rather than a multicast protocol. Within one connection, there are two participating parties. At a given point in time, one of them can send data and the other one receives data, but it supports actually full duplex data. That is, both parties can be senders and receivers at the same time, because you do not need to coordinate whose turn it is to send. Okay, this is called full duplex data flow. In fact, under the hood, the TCP protocol implementation implements two entirely separate state machines for the communication in those two directions. So TCP implements a reliable in-order byte stream. Okay, what does that mean? So reliable means that if any of the segments that are exchanged between two TCP endpoints are lost, then TCP will make sure that they are being retransmitted and then acknowledged by the other side. Second, in order means that bytes are received in the order in which they are sent. There are no message boundaries. There are no guarantees that if a chunk of byte is sent in a certain size, let's say 100 bytes, that the receiver will be able to receive those 100 bytes in one piece. The receiver may receive 50 and then later another 50, or the receiver may receive 50 and then 150 for the next 50 bytes already. This will become particularly important as you implement your project, but we will provide some classes, some C code to help you with this lack of message boundaries. Distinct from UDP, UDP preserves message boundaries. The TCP protocol is pipelined. Pipelined means that it is possible for a sender to send more data, have data in transit, even before previously sent data has been acknowledged. So transmission can proceed even while there is some data that has not yet been acknowledged. And the reason for this is to overcome propagation delay. If we waited for an acknowledgement before we would send the next packet, then if we have a connection that spans a large geographic distance, most of the time we would be waiting and the connection would be idle, even if it had very high bandwidth. So this data that has been sent but not yet acknowledged needs to be buffered by the sender. And so there are send buffers to accomplish this. This data that is in progress is buffered in case it has to be retransmitted. And there is also receive buffers where a TCP receiver can only receive data even though the application has not yet asked for it. So there's buffering at the sender and at the receiver. TCP is connection oriented. This means that it's not possible for a TCP sender to just start sending data. Rather, a TCP sender needs to first establish a connection through a process which is called a handshake. And it's called an exchange of control messages where the client that initiates a connection sends a request to establish a connection to a server that is responded with a acknowledgement, and then there's a third message that is being sent to establish this connection. And this connection establishment is required before data can be sent. TCP also, to add to this, so establishing a connection will also set up state inside the client and server implementation. That state persists while the connection is in progress. TCP provides flow control. Imagine you had a sender and a receiver, and the sender were to send data at a much faster rate than the receiver could read it and process it. In this case, this data would need to be buffered somewhere, but doing unlimited buffering raises a resource control issue, right? A resource management issue. So TCP supports flow control where senders back off automatically if they are sending data at a rate higher than that which can be processed by the receiver. So we can think of it as a bounded buffer, very similar to Unix pipes. There it was also the case that if somebody placed data into the pipe at a rate that was greater than the rate with which the pipe was drained, then the sender would be blocked. The same thing happens here. The sender may be blocked trying to send data if the receiver could not keep up. So flow control is something that protects um, applications that cannot process data as quickly as would be required from high rate senders. There's a second aspect, and that is that of congestion control. TCP also provide a way to protect the network from sending data at too high rates. So specifically, as we recall the discussion from packet switching, if multiple TCP connections use the same bottleneck link in a network, so you use the same router, then their packets have to compete for slots in the queue that is used to service the outgoing link. If the rate at which packets are received is too high, the queue will fill up, leading to queuing delay and eventually to packet loss. In those situations, TCP will back off and send at a lower rate, thereby protecting the network from congestion. TCP is a very, very rich protocol. The networking class I'm teaching, we usually spend 2 weeks just looking at the way in which TCP is implemented, how it does all these features. But on this slide here, I'm listing the core features of TCP that I think everyone should know and remember. This slide shows the TCP header. So this is the part that that is used by the TCP protocol to implement its reliable data protocol and to address the destination. So there's also a source and a destination port, as was the case for UDP. But TCP needs more information in its packet. For example, there is a sequence number that is necessary to make sure that data is kept in order and can be delivered to the receiver in the order in which it was sent. There's an acknowledgement number. That is the number that tells the other party how much of the data that was received from it has been received and is thereby acknowledged. There's the window size. That is the parameter where one party advertises to the other how many more data they're willing to receive before flow control has to kick in. And then there's a number of bits in here, control bits, for example, that those are necessary for connection establishment and teardown. For example, the SYN bit is the one that is set when an attempt is made to establish a connection. The finish bit would be during connection shutdown or teardown, and a number of other bits here as well. ACK means that the acknowledgement number here is valid, and in fact, data is being acknowledged. TCP also supports options for optional extensions, and those would come right after the header in this options area. Let's talk about how TCP and UDP do their addressing. I mentioned earlier that TCP and UDP do not have their own addresses, but rather they make use of addresses provided by the IP layer. But they do some addressing to make it possible to find out which application should be communicating, right? To which application data is directed or where it is coming from. And there can be multiple applications running in multiple processes on a machine or host. So the question is, if we have a process A on host H1, how does it communicate with process B on a different host H2? The answer is that this requires a quadruple of 2 addresses and 2 port numbers. So specifically, we have a source address, we have a source port number, a destination address, and a destination port number. So these addresses here are either IP version 4 or IP version 6 addresses. IP version 4 addresses are essentially 32-bit numbers, and IP version 6 addresses are essentially 128-bit numbers. IP version 4 addresses are such you've probably seen them around. So they're typically written in the so-called dot notation. So 3 dots are being used to separate 4, and these are decimal numbers. So an example 172.217.9.196 is an example of an IP version 4 address. Port numbers on this is by the way a current address that goes to google.com. Port numbers are simple 16-bit numbers. Okay, so we have at most 65,536 of them. Not all of them can in fact be used. So they form a namespace that is shared on a particular machine. So on a shared machine such as rlogin, you will in fact be sharing the port number namespace with other users on this machine. The namespace, however, is per address and protocol. So there's a different namespace for TCP as there is for UDP, and in fact also a different namespace for IP version 4 versus IP version 6. Sometimes that's written as shown here, say 80/TCP that says port number 80 for the TCP IP version 4 protocol, or 53 UDP6 that would be say port number 53, and the protocol that's being used is UDP over IP version 6. Those port numbers, there are conventions for what those port numbers are used, and there's a file called etc services for commonly used port numbers. You know some port numbers probably. For example, HTTPS by default uses port number 443, HTTP port number 80, so a number of other well-known ones, SSH 22 and so on. So a stream is characterized by a quadruple, and that's particularly important when thinking about how an incoming packet, that may be a TCP or UDP packet, is delivered to an application that is waiting for it. So those 4 parameters, which are part of the packet that's being delivered, are used to find out which connection a packet belongs to. And more specifically, in the case of UDP, it is only the destination address and the destination port that is used. However, in the case of TCP, which supports multiple connections leading to the same destination address and destination port, it is necessary to use the entire quadruple. There's also a notion of local versus remote, or remote also called a peer address in this case, as part of the API. So in this case, the local address is a combination of, let's say, the source address and source port if you are the sender, and if you are the receiver, then the the peer address would be the source address in this case. This depends on your perspective, but those are the terms that are being used: local and remote address, and those addresses are always pairs between address and port number. Let's talk about IP addresses some more. Here's a screenshot I found online, which is from a Hollywood movie, I think Iron Man 3 in this case. And you can see what's wrong with this picture if you look closely. Well, that is here the IP address. Of course, it's not a real IP address because an IP version 4 address is 4 8-bit numbers, and 455, of course, is not an 8-bit number in decimal representation. In fact, there is a whole community online that looks at sort of snafus by Hollywood movies. Now, you may argue that perhaps the makers of this movie intentionally chose to use an invalid address, because if they had chosen an actual address, that may have been conflicted with the address of an existing network provider. So this leads to the question of, how are IP addresses assigned? Are they assigned randomly? And then if an IP address is assigned to a particular organization, how does this IP address make use of it? And this is an interesting topic that that is not quite obvious how this works. So the first thing is, the question is, how does IP version 4 addressing work, right? Can anybody just grab an IP address, say this is my IP address, and use it? The answer to that is no. IP addresses are being assigned. There is a global authority that says this organization gets this set of IP addresses. and only those, right? So they're globally unique. Otherwise, the internet would not work. But IP addresses within this organization can actually not be assigned arbitrarily. And the reason for this is that IP addresses, strictly speaking, do not denote hosts, but rather they denote interfaces on hosts. Now, what's the difference? So let's say a host may be your laptop, but on this laptop, you may have a wireless Wi-Fi interface, and you may also have an interface that is being used when you plug your laptop into an Ethernet port. Other machines, login machines, for example, they have multiple Ethernet ports because they're connected to multiple networks. And internet routers, even more so, because they may be connected to across multiple links. So here's an example. Here's a router that is connected to 1, 2, 3 different interfaces. So these interfaces typically are something physical, right? So maybe a different network interface controllers, also called line cards, and so on. Now, an IP address denotes an interface. So a machine that has multiple interfaces needs multiple IP addresses. Each interface is connected to what is referred to as a subnet or subnetwork. And these are shown here in blue in this picture, which is also taken from the book by Jim Carouse and Keith Ross. So now the question then is, okay, so can I arbitrarily assign IP addresses to these subnets? The answer is no. Within one connected subnets, the IP addresses that are being used need to share a common prefix. So prefix here means that if I took this IP address and I wrote it down from left to the right, all the 32 bits, then the addresses that are part of one subnet need to share a prefix. Let's look at an example. So here's a subnet here at the top, and all the addresses in this subnet share the prefix 223.1.1. Out of this prefix, the first 24 bits are shared. We write this down by saying 223.1.1.0/24. So which addresses would be included in the subnet? Well, it would be the addresses from .0 all the way to .255. This distinction between which bits in the address are being used to denote or address interfaces within the subnetwork and which ones are constant is also referred to as the net mask, which is something that you sometimes may have to enter manually when you configure networking on a computer. So in this case here, the net mask would be a bit mask, and it would be all 1 bits for the first 24 bits, and then 0 bits here, and that is equivalent to the so-called /24 notation. Now you may wonder, so depending on where you make the split, that depends on how many hosts you can have on that subnetwork. We also need subnetworks here for these connections. So for example, to connect these two routers, we use a subnetwork that shares a prefix 223.1.9.2 and .1. We also share a prefix here. So we can do this division arbitrarily. For example, I could define a subnetwork 223.1.70/30 if I'm willing to use the first 30 bit of the address to denote the prefix that is common to this subnetwork, and then the last 2 bits to address hosts in there. So in this case, this would be 4 hosts from .0 to .3, and the net mask accordingly would be 256, which has 2 zeros at the end in its binary representation. So IP subnets share a common prefix. And in fact, when it comes to performing routing on the internet so that everyone in the internet knows where to send a given packet, the prefix of a subnet is used as the destination. Okay, so those subnets are in fact the routing destinations. When some routing is being done, then it will only look at this subnet prefix. Now, what about inside each subnet? How is routing done there? Well, routing is not done there. It is assumed that it is possible to reach every destination within one subnet without routing. So for example, if this router here, .3, wanted to send packets to .2 here, it could do so without needing to send this packet to another internet router. This is done through protocols that support this discovery at layer 2. For example, Ethernet has the ability for a host to ask, okay, where is dot dot 2? And then this host would respond and then obtain directly the link layer or Ethernet address and send it to the destination. So within each subnet, there is no routing. It is assumed that the destination can be reached directly. And for point-to-point links like here, I mean, it's clear there's only one way to send the data. But if the subnet, in fact, is for example, a local area network, then there has to be an additional protocol that is used at layer 2 that allows sending to such destinations. Um, I'm using the term CIDR here. So what does CIDR stand for? CIDR stands for classless inter-domain routing. The reason for this is that originally the designers of IP version 4 used a different scheme to decide which bits in an address belong to the address to subnet and which bits address a host on that subnet. So so-called class-based routing. There were class A, class B, class C networks, and they had a very rigid structure. Okay, so for example, a class A network would always split after 8 bits and therefore create very large subnets. As the IP version 4 address space became more filled, it was necessary to be more flexible in terms of where to make that boundary between the subnet address and the so-called host portion of the address. And that was accomplished using a CIDR, which was in fact introduced in the 1990s. Let's look at an example. This is an example I used to several years ago give on an exam in a graduate class. You're hired as a network administrator by some small company, and you ask for an allotment of IP addresses, and you were given a small /24 subnet at this address, 191.23.25. And you have two sites. They each have a LAN, maybe using Ethernet, with 60 and 120 machines, and you have a point-to-point connections that connects to an edge router at your ISP. Now your task is to use your allotted budget of IP addresses and assign them to each subnet subject to the constraints that I had mentioned on the previous slide, which is that all the machines on one subnet share a common prefix. Now this example is theoretical because this IP address is actually no longer available. I just looked it up. It belongs now to an ISP in Brazil. Okay, here's the solution. So in this case, we have three sites. This is one side here. The other side is shown on this side here. And this is the edge router that connects to the internet. And so one way in which the addresses here could have been split up is to assign one subnet starting at .0 and use 25 bits for the network address here. So this would include machines from .0 all the way up to 127, and it's enough space to fit 120. It is custom to assign address .1, although it's not necessary, it's a custom, to the interface that is connected to the router that connects you upstream. And this is also referred to as the default gateway. When a machine is configured in this network, either manually or automatically, each machine is given this default gateway, and so then it knows that if it wants to send an IP packet to a destination that is not part of the same subnet, it needs to be sent to this default gateway so that can then be forwarded or routed towards its destination on the internet. Now the other side here in this case might be from 128 and it might be using 26 bits. So this would be from 128 to 191. There's enough space to accommodate 60 machines. And that leaves us with about 64 addresses. And these addresses, for example, could be used for these peer-to-peer links here, maybe 192/30, which would include 193 and 194 for this connection. And then maybe using the next /30 for this peer-to-peer link. As a side note, so it used to be the case that for a subnet, so subnet is a power of 2, but the first and the last one couldn't be used. Okay, so .0 couldn't be used, and the one with all 1 bits couldn't be used because they use a special purpose, for example, for broadcasting on that network. But for peer-to-peer link, they relax this as a special case, so now you can actually have /31 here as well for those two addresses, because there's no point in wasting two addresses. Such things were introduced as the IP version 4 namespace got increasingly tight.